In this module, we are going to look at some examples of performing integration in one dimensions. So just to recall, we are interested in the problem of integral of f of x dx is equal to gx. And we will have f of x given, and we are trying to find g of x that corresponds to this. And if you should also recall that there are two types of integrals. There is the indefinite integral and there is the definite integral. And the difference between both of them is that the indefinite integral has no limits on this integral sign, while the definite has a limit going from, say, some value x1 to x2. So that would be given by g of x2 minus g of x1, while this indefinite integral will be written as integral f of x dx is equal to g of x plus some constant c. And we never care about what this constant is. We just write it as an unknown constant. And as you can see how this constant can be figured out if we actually know the limits of the integral. We are going to focus on this indefinite integral because once we do that, once we have figured out what is this g of x, calculating it for the definite integral just amounts to putting in the value of x1 and x2 and writing down g of x2 minus g of x1. So the name of the game here is to think about which g of x, so this is equivalent to saying that dg of x by dx is equal to f of x. So solving equation 1 is equivalent to equation 2. If you knew the answer to equation 2, then we could know the answer to equation 1. So what's the simplest thing we can think of? The simplest thing we can think of is what would be the integral of a constant integral of a dx. What would this be? So this would be ax plus some constant c. Why? Because d of ax by d of x is equal to a. So in this case, our f of x is a, our g of x is ax, and you can see that dg by dx indeed does give us a. And that's how we got it. So integral seems a bit funky at the beginning because there is no direct way of doing it. Actually, there is. You can go and use the limit as a sum formula that I showed you last time. Just like for derivatives, a rigorous way of doing it is to calculate the limit as x tends to 0. But in practice, the way it works is that you kind of remember a few basic derivatives, and then by using the chain rule and the product rule, you can calculate complicated derivatives. Similarly, it worked for integrals. You remember a few basic derivatives. By working back from them, you calculate the integrals. And then by using chain rules and product rules, which we will be looking at in the next module, you can calculate complicated integrals. So let's go to another one. If we had, let's say we are interested in the integral of x to the power n dx. What would this be? So this would be 1 by n plus 1 x to the power n plus 1 plus some constant c. The thing to keep in mind is this is valid if n is not equal to minus 1. And you can see why that is the case, because if n is equal to minus 1, then this would be a constant and this wouldn't work this way. This is an integral that shows up in chemistry quite a lot when we are thinking of things such as change in enthalpy during a chemical reaction. You will see this integral showing up a lot. What happens when n is equal to minus 1? Then we have integral 1 by x dx. You have to recall what is that function differentiating which we would get 1 by x. That function is log of x. So this is log x plus constant. This one also shows up in physical chemistry a lot, and you will see this in the associated exercises, how it shows up. Next one, let's try to think about the integral of sum of two functions, f of x plus g of x dx. This will be equal to the sum of the integrals themselves. So What does this mean in practice? It means, for example, if I asked you what is the integral of a plus 1 by x dx, we just saw a dx in example 1, and we saw 1 by x dx in example 3. All we need to do is to add both of them. So a dx was ax, 1 by x dx plus ln x. Now you might ask, what about the constants? Constant plus a constant is also a constant. So you don't have to write C1 plus C2. You just write down the C over here. So this rule, as you can see, is very, very useful. And immediately you can start, if you have a sum of some very complicated function. If you have, for example, let's look at another example. If you had something that looks like integral x plus x squared plus x cubed plus x to the power 4 dx, what would that be? I will give this in the exercise for you to think about, but use rule 4. Rule is a bad word. It's not really rule. It's just putting common sense in words. Plus rule 2 to get it. So rule 2 gives you the general value of this for any n. It tells you for x is n is equal to 1, n is equal to 2, and all you have to do is to add all of them, because this would apply not just for 2 functions, but for any number of functions. Okay, now let's go to another integral, which is extremely common in chemistry and physical sciences in general, which is the integral of an exponential a to the power ax dx. This will be given by 1 by a to the power ax. So this one is something where students tend to make mistakes often, because when you're differentiating e to the power ax by dx, the a comes in the numerator. That's what we have used here, but in the integration, since a comes in the numerator, we have 1 by a d e to the power ax by dx is equal to e to the power ax. So in the integral, it ends up showing in the denominator. So this is something, it's easy to make a mistake if you're not careful. Let's move on to the trigonometric function. There we have integral sine of ax dx is equal to minus 1 by a cos ax plus some constant c. Again, you can go back and differentiate this thing to check whether that it is true. And if you recall that while differentiating cos, we get a minus sign. So that's why integrating sine, we get a minus sign. But now if we were to integrate cos, we would not get a minus sign. This is again something that gets inverted between derivative and integrals, something to keep in mind. So once again, like in many of these things, you might ask, what's the point in me remembering all of this? I can just look it up on the internet. As a practicing scientist, I have the same question that I ask myself 20 times a day. Why do I know something? Why do I have to put it in my memory? Why, if I can just look it up on the internet? Let me assure you that it is still faster to have it in your head, certain basic rules. At some point it gets complicated, and it's best to look it up in the internet. But these things that we're doing in the modules are typically things that for an undergraduate chemistry or physics class, you will benefit a lot if you had a working command of these things without looking up the internet. You would still be able to do problems if you were looking up on the internet, but you will be much slower. You could use your time to do something else. So now let's look at a function which shows up in a lot of physics and chemistry, which is delta function. So delta of x minus x naught, you might have seen this in other modules, is something that looks as it at x naught, it is equal to infinity, and everywhere else it is 0. So it looks something like it's 0 everywhere else, but at infinity it is. So this is infinity, x is equal to x naught, and 0, x naught equal to x naught. So what is the integral of the delta function? If you recall, the whole idea behind an integral is the area under a curve. And the area under a delta function is 1. It's not obvious, but it will become obvious when we look at Gaussian functions, and the delta function is nothing but a Gaussian function that is progressively shrunk. So you have a Gaussian and you make it even tighter, and you make it tighter and tighter. As you make it tighter, keeping the area a constant, you get a peak that looks like that. So the peak is shrinking, it's moving in this direction, but it's also rising. So delta function is limit of a Gaussian of infinite height and very, very tiny zero-like width. So the integral of a Dirac, so this is a delta function. It's also called a Dirac delta function. The integral of a delta function is 1. And now sometimes one might have not a delta function, but a function, some other generic function multiplied by delta function. And in this case, the integral is the function calculated. As you can see, this thing is going to be 0 everywhere else except x is equal to x naught. So you can take out the f of x naught and keep it as delta of x minus x naught, because everywhere else, you know, it's not going to matter, and this becomes f of x naught. So this is a hand-waving proof of what happens when you have a delta function multiplied by some generic function. Next one we are going to look at, which is related to the delta function, is a Gaussian. We saw it in the function modules where we thought about the number of parameters it has. So a Gaussian integral shows up a lot in chemistry, in kinetics. There's a reason why it shows up in the probability module. You might have seen it. It's related to something called the central limit theorem. So without going to why the Gaussian is so important, all I can tell you is that it is important and it shows up in variety of contexts. So here, this definite integral, so we have put in the limits over here, and over all of these are actually definite integrals, because if your limit does not include, if the domain of integration does not include x naught, this answer will be something different. So I should put the limits in all of these. For Gaussian also we have a limit, and this one is square root of pi by a. I will provide a proof for this in the exercise, so you can try to do it yourself and then look at the proof. So let's look at the Gaussian function a bit more. How does it look like? A Gaussian function as a function of x would look something like, you can plot it using the basic idea of graphing that we discussed earlier. So it should be symmetric, because as you can see, x shows up only in even powers. It goes something like this. So here I am plotting the function f of x is equal to 1 by square root of pi e to the power minus x squared. So I have brought in the square root of pi in the denominator here, so that when I integrate it, this square root of pi that would have come in the numerator goes away and it becomes 1. And I have set a is equal to 1 in this Gaussian function. So we just saw that the area under all of this, as you go from minus infinity to infinity, would be 1 over area. So let's write it down. So minus infinity to infinity f of x dx would be 1 by square root of pi multiplied by square root of pi by a, square root of pi by a is equal to 1. So this will be 1. So we know the area from minus infinity to infinity under this function is 1. But what if I am interested in the area not from minus infinity to infinity, but from 0 to some arbitrary value x? So let's say I'm interested in this area, 0 to some value x. Let's use the color red here to show that we're talking about that. What would that be? That is, again, I will try to show it in the exercises. This has a very well-defined name. It's called the error function. It often shows up in variety of physics and chemistry problems where you're trying to look at how errors propagate in a system. And so you can see what is the definition of the error function. It is defined as, it is actually defined as 2 times this Gaussian over here. So there is a factor of 2. So the definition of error function is, and it's always written as ERF of x is equal to 2 times this integral. So what is that? So that becomes 2 by square root of pi 0 to x e to the power minus, and you might get confused by x being in the numerator and x being in the denominator. So one way to deal with that is to, instead of x, we can call it as, let's leave it there, but we can just change the name, what's in the name, as Shakespeare said. So we can call it e to the power minus t squared dt. So this is an important function that shows up. And now you can see that in other words, 2 by root pi integral 0 to, so let's actually look at this quantity and try to see what would it be. So instead of the integral from 0 to x, now let's think about the integral from x to infinity of e to the power minus t square dt multiplied by 2 by square root of pi. So how do we do that? That's going to be, we can separate it. So this is a generic property that we can look at it now. We can calculate the area of this area under this integral by separating it in two domains. We can think of the area going from 0 to infinity, e to the power minus t square dt. So what have we done here? We have not just considered x to infinity, we have considered 0 to infinity. So we have extra, we have overcounted the part going from 0 to x, right? So that's going to be e to the power minus t squared dt over, this part has been overcounted. So what we have used for this, I will describe it in a general setting in a moment, but let's look at this relation. So over here, so what were we trying to calculate? We were trying to calculate this integral, but for different limits. Instead of going from 0 to x, we are trying to go from x to infinity. So when we're trying to go from x to infinity, we thought of it as, okay, what would have happened if we went from 0 to infinity? What would have, and then we have to subtract out the part going from 0 to x. So if we went from 0 to infinity, we know what would have happened. We just saw it over here. And this one is the error function. So what did we get from this? We got that this thing is 1 and this thing is error function of x. So if we had to go from x to infinity, we could just calculate the error function going from 0 to x and subtract that from 1, and that would get it. So this has a special name. This is called complement of the error function, ERFC of x. So what we have just shown is ERFC of x is equal to 1 minus ERF of x. So this is just an example of how to integrate things. And but we used a general property here, which is that f of x dx from x1 to x2 can be split into f of x dx from x1 to x3 plus f of x dx from x3 to x2 if x1, x2, if x1 is less than x3 is less than x2. So visually, what does this mean? It means that we had some function that went like this. We started at x1 and we wanted to calculate the integral going from x1 to x2. That would be the same as picking any value of x3 in the middle and splitting it into two parts. First part would be this part, that would correspond to this integral, and the second part would be this part, that would correspond to this integral. So in the exercises, you will use this property to calculate integrals, some definite integrals, and see how it works. So these are some basic examples. In the next module, we will look at slightly more complicated examples. We will try to think of algebraic substitution. We will try to think of some more trigonometric transformations. And in the end, also we will think of something which is my favorite, which is called integration by parts, which is the product rule for derivatives relevant for integrations. And in the exercise module, in the exercises associated with this module and the next module, You have lots of practice problems, and it is critical that you work through them in order to become familiar with this material. Later on, when we do integration in multiple variables, you won't be able to make any progress unless and until you're comfortable with integration in one variable. And if you have mastered integration in one variable, integration in multiple variables, which is a very important chemistry, is actually quite easy. With that, thank you very much.